Hello everyone, my name is Partho Das, Assistant Professor, Department of Electrical Engineering, JIS College of Engineering, West Bengal, India. So first of all, welcome to my class. So today's class, as you can see, the topic is that distribution factor. This distribution factor is denoted by KD. It's denoted by KD. Okay, so here I have drawn a diagram, phasor diagram, so that I am going to explain after some time. So before explaining this phasor diagram, first we have to know what is the definition of pitch factor. Then there should be the explanation of that pitch factor. Then we are going for the derivation of the equation of a distribution factor. So first, the definition. So what is told, the ratio of the phasor sum of the EMF induced in all the coil distributed in a number of slots under one pole to the arithmetic sum of the EMF induced is known as the breadth factor or distribution factor. So this is the distribution factor. So when we are discussing about distribution factor, so there are two terms is very important to understand, otherwise we are not totally getting the concept of this distribution factor. That points are concentrated winding and distributed winding. So first of all, we have to know what is concentrated winding and what is distributed winding. As already stated, if all the coil sides of any one phase under one pole are bunched in one slot, the winding obtained is known as the concentrated winding. Once again I am repeating, if all the coil sides of any one phase under one pole are bunched in one slot, the winding obtained is known as the concentrated winding, and the total EMF induced is equal to arithmetic sum of the EMF induced in all the coils of one phase under one pole. So when we are discussing about the concentrated winding, so there we have to consider that the total EMF induced is equal to the arithmetic sum of the individual EMFs that will be induced in each coil side in under one phase under one pole. So as we have previously when we have done the pitch factor, there also we have seen that we have short pitch, then we have full pitch concept. Like this way, here also we have the concentrated winding. So first thing that we have to know, that is the concentrated winding. So already discussed the definition that all the coil sides of any one phase under one pole are bunched in one slot. The winding obtained is known as the concentrated winding. Okay, so like this way, one thing is that next thing that we have to know is the distributed winding. Distributed winding. So what is distributed winding? In order to obtain a better wave shapes, the coils are not concentrated. Okay, in real life, whatever machines we actually use, there we never use the concentrated winding. In general case, we use the distributed winding. Okay, so now what is the distributed winding? When the coils are not concentrated or bunched in one slot, that means whatever windings or coils are there, they are not concentrated or bunched in one slot, but they are distributed in a number of slots to form a polar groups under each pole. That means when the coils are not concentrated, not placed in one slot, but are distributed in a number of slots. They are distributed in the number of slots. As the stator, we have seen there are different slots here. semi-closed, closed, open slots. So there are different types of slots are there. So in that case, in those places, the windings are the coils are distributed to make a polar groups under each pole. So this winding, this kind of windings is actually known as the distributed winding. Okay. In such winding, the coils are placed from each other by a certain angle. Okay. In this case, the coils are placed from each other by a certain angle. The result is that the EMF induced in the coil sides of one phase is the adjacent slot under one pole are not in phase with each other but differ by an angle equal to the angular displacement of the slots. So the resultant EMF of all the coils of one phase under one pole would be the phasor sum. That means in one line is this in this case it will be the arithmetic sum, and in distribution winding we have the phasor sum. So just for now, remember this thing. In case of concentrated winding, whatever EMFs will be induced, all EMFs will be taken as a phasor sum, arithmetic sum, and in case of distributed winding we will consider the phasor sum. Okay. So first, before for the explanation, first see then as far we have understood this thing, concentrated winding and distributed winding. So let us see what is the expression for this distributed winding. So distributed winding KD is given by EMF induced in distributed winding by the arithmetic sum of components EMF. So it is basically the distributed winding EMFs, those are the phasor sum, and here will be the arithmetic sum of the concentrated winding. So that ratio is known as the distributed winding. So this thing we have to understand now how to find out. Okay. So to find out this expression, we have to consider something. Okay. So let us consider the number of slots per pole. Slots per pole, we are considering n, and now we are considering number of slots per pole per phase m. Now we are going to consider what is the EMF generation. So EMF induced EMF in each coil side is equal to EC. Okay, and as in case of distributed winding, there are whatever EMF is induced in each coil side, so in between them there are some angular displacement. So let us consider what should be the angular displacement. Say that there is the beta. So angular displacement between the slots, that we are considering as beta, where beta is equal to 180 degree by n. Okay. Now after considering those things, so what we have considered, slots per pole, that is n, number of slots, that is T, that is slots per pole per phase, that is m, induced EMF in each coil side, that we have considered EC, and angular displacement between the slot is b, that we have considered. Now coming to the diagram, so now we are going to understand so what the things we have considered and how we have to deal with that one. So the EMF induced in different coils of one phase under one pole are represented by side AC, CD, DE, which are in equal magnitudes but differ in phase by an angle beta from each other. Again I am telling you, now coming to this particular diagram, so what we have, these are the EMF, AC is a EMF, CD is a EMF, ED is a EMF. So like this way we have a n numbers of EMF is generated over there. So we are considering that this AC, CD and ED, those EMFs has same magnitude, these values are same, but they are differ from each other by an angle beta. See, this should be the angle, then there is a shipment like this way it should be going, and in between that there is a beta, like this way this is going like this way phasor, and it is shifted by an angle beta. So like this way everywhere there is a beta angle. So as we doesn't know the how many numbers of windings are there, coils are there, so that's why we are considering 2, 3 so for the calculation purpose only. Okay, now if bisects are drawn on AC, CD and DE, that means over AC, CD and DE, if we draw the bisects, they will meet, if we are drawing a bisects over there, and they will meet a point O, say a common point, that is O. We are considering over the bisects of this one, the bisects of these phasors are connecting to a point that is O. Clear? As you can see, the bisects of these phasors, the phasors are connecting to some point O. The point O would be the circumcenter of the circle having AC, CD, DE as the chords and representing the EMFs induced in the coils in different slots. Okay, so EMF induced in each coil side. So now what should be the EMF induced in each coil side? So EMF induced in each coil side, say we are considering that is E is equal to, this is the EMF, so what should be the value of this one? AC is equal to 2 of OA sine beta by 2. Okay, so now you can ask me how I have finded out this value. Okay, so the point is that, so just see this section, as we have done in the pitch factor calculation, geometrical calculation, here also that kind of a geometrical calculation. So can we consider this is a triangle? In the triangle AOC, if we draw a bisects, so and this angle is the beta. Okay, so what should be this angle? This will be the beta by 2, this will be the beta by 2, and now if we give a name, say P. So now in this particular triangle, we want to find out this value of AP. Now after finding out this value of AP, so what should be the value of AC? That is 2 times of this AP. Okay, now our purpose is to find out this value of this AP. So now we know, as you can see, AC is equal to 2 of AP. Okay, now if we can able to find out this value of AP, then we can find out the value of this AC. So now consider in the triangle AOP, this triangle we are considering, inside that what is the angle? This is beta by 2. So what is what is, sorry, not sine beta by 2. What is sine beta by 2? The sine beta by 2 is given by, so in this triangle sine beta by 2, this is the AP by, but we can write down OA. Okay, so what is AP then? AP is equal to OA sine beta by 2. So then from this concept, can we write down the AC is equal to 2 of OA sine beta by 2. So like this way we can write down AC is equal to 2 of A sine beta by 2. So this is the procedure how we can, if in each triangle there are several triangles that we can see, so in each triangle we can do the same thing and we can find out the value is same. So now, so what is the total arithmetic sum? So it is the EMF value of one coil side. So if we have the m numbers of, see there, number of slots per pole process we have considered, that is n. So what is the total EMF? So arithmetic sum is equal to m numbers we have, and one EMF has the value of this. So m into 2 into OA into sine beta by 2. Okay, so the resultant EMF induced in one polar group of one phase would be the phasor sum as represented by the phasor AB shown in the above figure. Okay, so the resultant, what should be the resultant? This one will be the resultant. See, as we can see, so this will be the resultant. So we are considering this is one EMF phasor. Okay, so like this, we in m numbers we have, so we know that this will be the EMF of all this EMF induced, the phasor sum of this EMF induced will be given by this line AB, correct? So the here we can say that the resultant EMF is given by it is actually the AB, this A to B, this line. So AB is given by 2 into OA into sine angle AOB by 2. Now again you can ask me from where I have getting this. Now see, as I have finded out the value like this expression, now can we consider this is the total triangle, it is a triangle, this is a triangle, okay, and in that triangle, like the same method we have followed over here, so like that way we can again find out the value of this angle is this. AB is equal to 2 into OA into sine AOB, this total angle by 2, so m beta by 2. Okay, so this total angle is m beta, so half of this total AOB angle is, so this total AOB angle is it is m beta. So what is m beta by, so AOB by 2 means m beta by 2. So the expression of this AB will appear like 2 into OA into sine m beta by 2, correct? So now coming to that expression, so this expression we are coming, now we know the EMF induced in the distributed winding, we know, so what is that? This one, and arithmetic sum of the components, so that is also known to us, this one. So make a ratio of that one, so KD is equal to 2 into OA into sine m beta by 2 by, here is the arithmetic sum, that is equal to m into 2 into OA into sine beta by 2. So what will you cancel out? 2 OA cancel out. So what is the remaining? KD is equal to sine m beta by 2 by m into sine beta by 2. So this is the actual expression we have in case of distribution factor. Okay, so this is the distribution factor. Now if we consider, the flux distribution contains space harmonics, the slot angular pitch beta on the fundamental scale would become R beta for the rth harmonic component, and thus the distribution factor can be rewritten like this way. So we can rewrite this equation, that is KD is equal to sine R m beta by 2 by m sine R beta by 2. So if we include the harmonic inside that, then the equation is like this, and otherwise the general expression for this distribution factor is this. So this is like this way we have to understand the distribution factor and its expression. It is very much important for your semester also. So in the next class we are going to do different problems over this distribution factor and the pitch factor. So this is all for today. Thank you.